Hello and welcome. Every single time you snap a photo, you're kicking off this unbelievable journey. It's a super high-speed trip that turns actual physical light into a digital file in, less than the blink of an eye. So let's pull back the curtain and dive into that hidden world right behind the lens.
It feels completely instant, doesn't it? Just a click. But underneath that super simple action, there is this whole cascade of physics and computation that is, honestly, it's mind-blowing. In this explainer, we're going to break down that exact process, step by step. We're going to follow this journey through 5 key stages. We'll start with how light becomes a signal, then how we build the digital image from that. After that, we'll look at perfecting the pixels, then painting it all with code, and finally, we'll cover the art of compression. All right, let's jump right in. Okay, so our journey starts right here, in the real world. Every photo, every single one, begins with a light source. The sun, a lamp, whatever, bouncing off a subject and flying straight into your camera. So here's that crucial first step. Light energy, which is really just photons, smacks into your camera's sensor. Now, this sensor is basically a translator. It does this amazing thing where it converts that light energy into a raw electrical voltage. The brighter the light that hits it, the higher the voltage. This analog signal, it's like the very first ghost of our future image. Now, what's really cool is how we do that capturing. You see, something like a flatbed scanner uses a sensor strip that has to physically move across the page. But your camera, it uses a sensor array. Just think of it as a massive grid of tiny light detectors that captures the entire scene all at once. No motion needed. That right there is the key to freezing a moment in time. Okay, so we've got this continuous electrical signal. But here's the thing. Computers don't speak analog. They speak in numbers, in ones and zeros. So now we have to perform a translation. The first part of that translation is called sampling. The easiest way to think about this is to imagine laying a giant piece of graph paper over the scene you're capturing. Every single little square on that paper is going to become 1 pixel. And it's pretty simple. The more squares you have on your grid, the more detail you're going to be able to capture. So now that we've got our grid, we need to figure out what to put in each square. That step is called quantization. We measure the voltage we captured for each of those points on our grid, and we assign it a number from a limited set of options. The analogy here is perfect. It's just like having a box of crayons, and for each square on your graph paper, you pick the shade that's the closest match. And these 2 steps, sampling and quantization, brilliantly set up the 2 main types of resolution. Spatial resolution is all about how many pixels you have. That's your sampling, the density of your graph paper grid. Then you have intensity resolution, which is about how many shades or how many crayons you have for each pixel. That comes from quantization. You absolutely need both for a high-quality image. Now, the raw digital image we've just created, well, it's not perfect. The real world and the whole capture process, they introduce flaws and imperfections. So now we've got to clean it up. And when we talk about improving an image, there are really 2 different approaches. On one hand, you have image restoration. That's pure objective science, using smart algorithms to remove known problems, like motion blur or sensor noise. On the other hand, you have image enhancement. That's more of a subjective art. It's about making the image look better to us by tweaking things like contrast or sharpness. And here's a simple but really critical fact. Noise is absolutely everywhere. It's that random, grainy static you sometimes see in photos, especially when you're shooting in low light. So these advanced restoration techniques are often designed specifically to hunt down and reduce that unavoidable digital static, giving us a much cleaner foundation to work with. So far, we've mostly been talking about intensity and brightness, which is basically a black and white image. But now comes the real magic. Let's add some color. What's so cool is that digital color actually works by copying our own biology. Our eyes have special cells called cones that are sensitive to red, green, and blue light. So the RGB color model does the exact same thing. It assigns 3 different numbers to every single pixel, 1 for how much red is in it, 1 for green, and 1 for blue. And when you combine those 3 values, with each one having 256 possible levels, well, you get this, over 16.7 million possible colors for every single pixel. It is a truly enormous digital palette, and it's what allows us to represent all the subtle nuances of the real world with incredible fidelity. It's just amazing. We did it. We have a beautiful, high-resolution, full-color image. But there's a huge problem. The file is absolutely massive. So the final step in our journey is to make it small enough to actually use. The secret to all of this is targeting something called redundancy. And redundancy is just any data in the file that's either repetitive or that our eyes aren't going to miss anyway. The entire goal of compression is to intelligently throw away data without anyone even noticing it's gone. So compression algorithms are basically hunters, and they're looking for three main kinds of waste. The first is just inefficient coding, but the big ones are next. There's spatial redundancy. Think of a huge blue sky. Thousands of pixels are all nearly identical. So instead of describing each one, you can just say, hey, this whole block is pretty much this shade of blue. And finally, there's irrelevant information, stuff our eyes aren't even sensitive enough to see. For example, our eyes are way better at noticing changes in brightness than small changes in color. So you can throw out a lot of color detail and we'll never know the difference. And the result is, well, it's dramatic. A pretty standard 10-to-1 compression ratio means that 90% of the original data has been identified as redundant and just removed. This is how we can send photos so easily across the internet. We're keeping what our eyes need, and we're just tossing the rest. And there you have it. We went from a wave of light all the way to a smart, compressed, and colorful JPEG file. The entire, incredibly complex journey is finally complete, and that photo is now ready to be shared with the world. So the next time you take a picture, maybe you'll think about that incredible journey it just took. And it leaves us with a pretty big thought. We've basically figured out how to digitize the sense of sight. So what's next? What's on the horizon? Touch? Smell? The journey of turning our reality into data is, believe me, far from over.